Hello friends, I welcome you in lecture number 12 on logic. In lecture number 11, we have discussed certain basic logical equivalencies or basic logical laws, and using those logical laws we can prove that two propositions are equivalent. We have used the truth table to show that two propositions are logically equivalent in previous lectures, but we are going to discuss another method of showing that two propositions are logically equivalent, and that method is sometimes easy and less time consuming as compared to the method of truth table. In particular, when we have more than two variables, then it is not comfortable to use truth table to prove that two statements are logically equivalent. Instead of that, we can use certain basic logical laws, and using them we can show that two propositions are logically equivalent. So that we will understand with the help of example, but we just recall certain basic logical equivalencies which we are going to use. We are familiar with De Morgan's laws, that negation of P or Q is equivalent to negation P and negation Q. Another statement of De Morgan law you can write simply by replacing or by and by or. So this is negation P or negation Q. We are familiar with distributive laws also. P and Q or R is equivalent to P and Q or P and R. We are going in this way, P and Q, we keep this in between, then P and R. And we are familiar with commutative law also, that P or Q is equivalent to Q or P. Similarly, this P and Q is equivalent to Q and P. So using commutative laws we can rewrite this distributive law in this way also. Using this commutative law I can rewrite this as Q or R and P, and this I can rewrite as Q and P. Here I have or in between, and then R and P. So Q and P or R and P, and you can see here also if we apply commutative law, then these two are same. P and Q is equivalent to Q and P, P and R is equivalent to R and P. So we will remember all these laws which are easy to remember, and we are going to apply them frequently in upcoming lectures. We have seen this also, that this conditional implication P implies Q is logically equivalent to negation P or Q, that is negation of first proposition or second proposition. So whenever we require, we will use all these logical equivalencies to prove that two compound propositions are logically equivalent. We have seen associative law also, that is if I am writing Q or R in the bracket and here I am writing P and Q in the bracket, then these two are logically equivalent, and this is true for AND operator also, P and Q and R. So remember all these logical equivalencies, and using them we can show that two compound propositions are logically equivalent. So first we prove this, that P implies Q implies R is logically equivalent to P and Q implies R. So first we start with this P implies Q implies R, and now we use this logical equivalence that P implies Q is equivalent to negation P or Q. So first I am applying for this Q implies R, that I can rewrite as negation Q or R, negation of first variable or second variable. Here first variable is P, so here I am writing negation P. Here first variable is Q, so I write negation Q and or R. We again apply that equivalence. Here if we wish, we can write in the bracket what we have applied. P implies Q is equivalent to negation of P or Q. Now we again apply this logical equivalence to this implication. Here first variable is P, second variable is negation Q or R. So first I have to write the negation of first variable, that is negation of P or second variable. So I write this as it is, negation Q or R. And I will keep in mind that I want to prove that this is logically equivalent to this one. So here I require P and Q implies R. That means if you apply this law to this one, then you can see that this is logically equivalent to negation of P and Q or R. So I will require, or I will try to find out, or I will try to obtain this term in this. Here I have now negation P or negation Q and R, and here I require negation of P and Q. So for that I will apply associative law. I will combine these two now, negation P or negation Q, and here I will write this is, I am applying associative property, so I will simply change the grouping of this. Here I have taken group of negation Q and R, here I am taking these two in the bracket. So this is using associative law. And here I require, you can see what I require here. I require negation of P and Q. So if you remember De Morgan's law, this is equivalent to negation P or negation Q, and is replaced by or. Therefore I can replace negation P or negation Q by negation of P and Q using De Morgan's law. So I am applying De Morgan's law now, negation of P and Q or R. Here I am using De Morgan's law. Using De Morgan's law, and now you can see this is nothing but P and Q implies R. Using this logical equivalence, P implies Q is equivalent to negation P or Q. Here instead of P we have P and Q, so negation of P and Q or R. So we are applying in this way, negation P or Q is equivalent to this, and this is what we wanted to prove, P and Q implies R. So you can see within few steps I am able to prove that these two are logically equivalent. Suppose you use the truth table, then you have to prepare all these things. Suppose I want to use truth table to show that these two are logically equivalent. I have to write P, Q, R, then I have to find out Q implies R, then I have to find out P implies Q implies R, then P and Q, and then P and Q implies R. So using this method also we can show that two statements are logically equivalent. All we have to remember is certain basic logical equivalences. We applied De Morgan's law and we applied associative law and we applied this logical equivalence. We consider another example to prove this one. Here we prove that this compound proposition is logically equivalent to R. So we start by writing this one, negation P and negation Q and R. This is in the bracket, or Q and R, or P and R. And I will keep in mind that I want to prove that this is logically equivalent to small r. Now here if you observe, if you can see here I have R common here, so I can use this. Suppose I write Q or P. Here I have Q, here I have P, and here I have or. Q or P, and here Q and R and P and R, so I am writing and R. So using distributive law I can rewrite this as Q and R or P and R. Now you can see here I have Q and R or P and R, so that I will replace by Q or P and R. And here I can apply associative law and I can combine this negation P and negation Q and R. This is in the bracket, and this I am replacing by Q or P and R. And what I have applied here using distributive law. I have to mention that whatever logical law I am applying using distributive law, that is Q or P and R is logically equivalent to Q and R or P and R. Now if you observe here, here also I have R, here also I have R, here I have negation P and negation Q, here I have P or Q. So if I wish, again I can apply distributive law, and it is this type of situation now, that P and R or Q and R, this is logically equivalent to P or Q and R. Here I have R common, so that I am writing here, and here I have or, so P or Q and R, and you can see this is P and R or Q and R. We have seen this type of distributive laws so far, P or Q and R. Using commutative property I can write this as R and P or Q, and that is R and P or R and Q, and this I can rewrite using commutative property as R and P can be written as P and R or here Q and R. So now you can see P or Q and R is logically equivalent to P and R or Q and R. So that I will apply again here. Let me remove this. Now you can compare these two. Here instead of P I have this quantity negation P and negation Q. Instead of Q I have Q or P, and R is there. So now this is equivalent to this one, So this is equivalent to P or Q. Instead of P I have negation P and negation Q, or instead of Q I have Q or P here, Q or P, and outside the bracket I will write and R. I have applied this distributive law in a reverse way. P and R, instead of P I have negation P and negation Q, or Q and R, instead of Q I have Q or P, and this is equivalent to P or Q and R. So I have written this or this and R. Or you can see here I have R, so I will write R with and R I have written outside, and I will join these two by OR. Now what is this? This is, if I use De Morgan's law, then this is equivalent to negation of P or Q. Using De Morgan's law, negation of P or Q is equivalent to negation P and negation Q, and here I have Q or P, that I can rewrite as P or Q using commutative law, and here and R. Now what is this is equivalent to what? So if you recall, we have seen that if I have P or negation P, then what is it? So we can use simply truth table. P has two possibilities, true or false. Negation P is opposite, F and T, and I am joining these two by OR operator. So here this is true, therefore this is true, here this is true, therefore this is true. That means P or negation P is always true, and the proposition which is always true, that we denote by capital T. Therefore here I will write capital T, this is logically equivalent to capital T and R. Now capital T and R, this is now capital T. R has two possibilities, either true or false, and now I have capital T here, and I join it by AND operator with R. So here both are true, therefore this is true, and here this is true but this is false, so this is false. So you can see T and R has same columns, therefore T and R is logically equivalent to R. So now we have proved that this is logically equivalent to propositional variable R, and we have used many logical laws here. We have used distributive law, we have used commutative property, we have used this property, P or negation P is equivalent to T, and we have used De Morgan's law also. Here you have to mention in the bracket, here we have used De Morgan's law. So this is another way to prove that given compound propositions are logically equivalent using basic logical laws or equivalences. And if you are not comfortable with this, you can use truth table also, but you can see, suppose I want to use truth table to prove that these two propositions are logically equivalent, then you have to prepare so many columns for PQR, then columns for negation P, negation Q, then columns for negation Q and R, then column for these two Q and R, P and R, then column for these two. So that will be more time consuming as compared to this. So if you are comfortable, you can use this method also to prove that given propositions are logically equivalent. Otherwise you can use truth table also. And in examination, suppose they have mentioned that using truth table prove that two propositions are logically equivalent, then you have to use truth table only. But if it is not specified, then either you can use truth table or you can use logic equivalences, basic logical equivalences to prove that given compound propositions are logically equivalent. So this is all about this session. I hope you like it. Thanks for watching.